Hello and welcome to Appian Elevate 2025. I'm excited to share with you my presentation on performance optimization for desktop cloud apps. And I've been working as product manager at Appian Latam since 2019, while also creating courses in Spanish and serving as an instructor. Over the past few years, I've designed and delivered several training programs, including moving to PowerBuilder 2022 R3 and building desktop to cloud solutions with PowerBuilder and SnapDevelop 2022 R3. My most recent course is Moving to PowerBuilder 2025, which reflects the latest advancements in the product. My journey with PowerBuilder goes back quite a while. I became a Sybase PowerBuilder certified professional in 2005, and since then I've enjoyed helping developers modernize and transition their applications to the cloud. In my professional experience, I've worked with PowerBuilder, PowerServer, .NET Data Store, and Node.js. About Dora Sistemas, it is the Appian master distributor in Latin America with offices in Mexico, Peru, and Colombia. We provide technical support in Spanish across the region, offer specialized courses on PowerBuilder, PowerServer, and SnapDevelop, and deliver software outsourcing services. This presentation was prepared by community volunteers and reflects their own views, not Appian's. Please respect the copyright. Do not share or reproduce without permission. Session agenda. We'll start by reviewing the key variables that affect the performance of PowerBuilder applications, both in client, server, and PowerServer environments. Next, we'll go over some strategies for achieving rock-solid cloud app performance on the internet. In this section, we'll focus on three important aspects: latency and bandwidth, recursive SQL, and data volume. And finally, we'll wrap up with some Q&A time so you can share your questions. Let's start here. As you can see, we'll be focusing on client or server on a LAN and PowerServer over the WAN or Internet. When it comes to performance, there are a few key variables that can really make a difference: local computing, recursive SQL, or data-intensive operations. And of course, the network. These are the main factors to keep in mind as we move forward. Here's the idea. Each star represents how strongly a variable impacts performance. Starting with local computing, both client-server and PowerServer rely on the user's machine, but the impact is moderate, not the main factor. For client-server apps on a LAN, the real impact comes from SQL. Recursive queries or data-intensive operations can slow things down. The network, however, matters very little because the LAN is fast and stable. Now, with PowerServer over the Internet, the picture changes. Both data-intensive SQL and recursive queries become major factors, carrying a very similar weight in how they affect performance. On top of that, the network itself is also critical, since everything depends on WAN or Internet conditions. So in short, local computing matters a bit in both, but on LAN, SQL dominates, while over the Internet, SQL plus the network make the biggest difference. When we talk about the network, two key concepts matter most: latency and bandwidth. Latency is simply the delay, how long it takes for a data packet to travel from one point to another. It's measured in milliseconds and directly impacts responsiveness. Bandwidth, on the other hand, is the capacity, how much data can be transferred per second. It's measured in bits per second, and it defines how much information can flow at once. So, in short, latency is about speed of response. Bandwidth is about volume of data. Both are essential for performance in applications running over the Internet. Here you can see some reference values. First, latency. On a LAN, it's very low, around 1 millisecond, while over the internet it typically ranges from 20 to 100 milliseconds. Next, bandwidth. In a LAN, it's much higher, from 1 to 10 gigabits per second, while over the internet it usually drops to about 20 to 125 megabits per second. Finally, if we compare both, latency on the internet can be 20 to 100 times higher, and bandwidth can be 8 to 80 times lower than on a LAN. Keep in mind these values are just referential, but they clearly show the gap between local and internet environments. Keeping in mind these two variables, latency and bandwidth, that can strongly impact our PowerServer applications over the internet, we need to focus on optimizing how information is exchanged between the client and the PowerServer web API, and also between the web API and the database. On the client side, we should review objects or SQL code in the application that might be recursive or data intensive. For example, embedded SQL, stored procedures or database functions, data window or data store functions, transaction functions like syntax from SQL, or calls to external web services. In a moment, we'll look at how to improve these areas, especially where inefficient practices can hurt performance in an internet environment. And when it comes to the web API's communication with the database, the best practice is to keep both within the same LAN on a stable, high-speed, low-latency network. Now we'll see how recursive SQL can impact the performance of a PowerServer app over the internet. In general, recursive server calls can be risky because they may quickly generate a large number of requests, what we call network chatter, which degrades overall performance. Let's compare two scenarios. In the first one, a traditional client-server app runs a recursive workload of 10 loops or round trips. With a standard latency of about 1 millisecond per trip to the database, the total time is about 10 milliseconds to complete the task. Now, if we analyze the same workload in a PowerServer app, we need to consider two latency segments: client to web API plus web API to database. Using average values, the latency from client to web API might be around 50 milliseconds, and the web API to database latency about 1 millisecond. So, across 10 loops, the total time is about 510 milliseconds. So what can we conclude? Recursive SQL operations that don't matter much on a LAN can become costly over the internet. The more round trips, the more latency multiplies, and performance can drop dramatically. That's why reducing recursive calls and minimizing network chatter is a key optimization strategy for PowerServer apps. To ensure your Power Builder applications perform well in a cloud environment, at a high level, your code needs to be written such that the server calls is minimized or relocated to the middle tier or backend. We'll see how to optimize calls in embedded SQLs. DataWindow computed fields calling PowerScript with embedded SQL, and using merging sending multiple requests in one call with PowerServerLabel. Let's start with a simple example of recursive processing in embedded SQL. The original script written for client-server might follow this algorithm. First, a cursor is declared on the order detail table. Second, a loop runs through all the records in the cursor on the client side. For each record, it calls an SQL update statement to modify order detail data. Each call goes directly to the database. This means that if the loop has 1,000 records, the process will make 1,000 trips to the database. Third, the script either cancels the transaction in case of an error or commits once the loop is completed. This implementation is not optimal in an internet environment. A workaround could look like this. First, retrieve the order detail records into a data window or data store. Second, loop through the records in the data window. As you go, update the order detail data using the setItem function, which ensures the changes remain local. Third, perform the update function, then the commit or rollback, depending on the result. This change makes a big difference in performance because it avoids making 1,000 separate calls to the server as the original script does. Another recursive SQL scenario can happen in data windows when computed fields trigger PowerScript calls with embedded SQL. Data windows with this type of implementation can negatively impact the performance of our app when retrieving records. This happens because once the data is fetched on the client side, the PowerBuilder runtime will execute the PowerScript function record by record. In other words, recursively. A couple of ideas we can apply are: 1. Change the data window SQL to join related tables to get data directly. And 2. Retrieve all required data to a data store and modify the user function to get data from the data store instead of from the database. By using these or similar approaches, we can eliminate the original recursive SQL. This third scenario is not exactly about recursion, but rather about multiple requests. When we have a script that performs multiple operations against the database, whether through embedded SQL calls or data window functions, as in this example that uses 3 data windows to update data through the update function, we can optimize this implementation by using the PowerServerLabel object. If we leave the script as it is, it would require 3 synchronous calls from the client side. Only after all 3 calls are executed would the app check whether to perform a commit or rollback, depending on a status variable. PowerServerLabel allows us to group these update function calls or SQL statements into a single request. We start the grouping process with the startMerge function, where we can add parameter 1. This parameter is the stop mode, which tells the app to stop executing the remaining SQL scripts if an error occurs. After placing all the calls that generate SQL statements, we call the endMerge function to close the group. At this point, the app sends the request to the PowerServer Web API. Once execution is complete, we can analyze the result, which comes back in an array of PowerServer result objects. Each element in this array has properties such as SQL code and SQL error text. And in this example, each index corresponds to one of the update calls that was part of the PowerServerLabel group. This demo was developed in PowerBuilder 2025, and it works with SQL Anywhere, both running inside a virtual machine on Azure. For the demo, I first checked the latency from my PC to the server using the curl command with the time connect parameter. This command can be useful if you cannot be in the server. We can see that the latency is about 140 milliseconds. Now in the PowerBuilder IDE, we have a window with 3 tabs. Each tab contains an exercise, similar to what we showed earlier. The idea is to compare the response times of the traditional client-server call versus a workaround. The same process, but optimized for an internet environment. Each call is measured in milliseconds. In every tab, the bottoms labeled original are implemented in the classic way for a LAN environment, meaning they don't account for the negative impact of recursion. The bottoms labeled workaround are optimized for an internet environment. The first exercise compares a recursive call using the SQL update statement directly in each cursor iteration. We want to display the rows visually, only measure elapsed time. Then we run a workaround with the same number of rows using a data window. In each iteration, we'll call the setItem function, and once all iterations are done, we save the data with the update function of the data window. Now we try this first exercise by running my app that is already deployed in the cloud. When running both processes a few times, we see that the workaround option is almost 3 times faster than the second, with only 50 records processed. The second exercise compares data retrieval in a data window that contains a computed field calling a PowerScript function to get region description. This function receives a parameter indicating whether it should execute an SQL statement to get the region name for each record or retrieve the name from a data store that has been previously loaded into memory. The last exercise is a process that saves data from 3 data windows. The regional option calls the update function synchronously or sequentially, which in this example means it will make 3 separate calls to the PowerServerLabel API to complete the 3 updates. Meanwhile, the workaround option uses the PowerServerLabel object and its functions start merge and end merge to group the 3 updates into a single call to the PowerServerLabel API. We also review the performance difference between both exercises. Now we run our cloud app again. We wait a moment and select the second tab. We always start with the original client-server call. The number of records is only 10, enough to clearly see the big difference in performance. Here we can see it took approximately 28 seconds. Now we call the workaround, which uses a data store in memory with the data for the computed field. It took just over 1 second, almost 20 times faster compared to the original call. We test again to see if the difference remains or if the initial delay was just due to the database connection in startup. This call took about the same time as the first one. Let's check the workaround once more. The significant difference is confirmed, achieved simply by adjusting how the data is retrieved for the PowerScript function. Now we'll see the last exercise using PowerServerLabel. We retrieve the data to be modified and then edit 1 record in each data window. Next, we run the original process, which takes almost 2 seconds. We then restore the modified data to save it using the workaround. We can see it takes about 1.5 seconds, which shows it is about 16% faster. Once you are certain the slowdown is not caused by excessive server calls, then you can consider reducing the size of data transmission. You can apply these recommendations. Retrieve data gradually to reduce load and improve responsiveness. Select only the necessary columns to optimize queries. And configuring request header for large data. Retrieve data gradually. Because retrieving very large data volumes, for example 1 million rows, would affect performance. And since the retrieve as needed and rows to disk options are not supported in PowerServer apps, you can use the following options to further filter the data at the source than on the client side. Add or improve the where clause in the SQL statement to retrieve only the data needed. Use a next button to the data window and modify the SQL query to support pagination, using Ronon for Oracle Database and Top for SQL Server. You can also create a button to paginate records from a web API using retrieve by page function of .NET Data Store API or using page function of SQL Query Builder object. This last option is native to Snap objects. Let's check out some practical examples of how to implement a next button to retrieve data gradually. One option is to retrieve records into a data window, but first modify the SQL query to support pagination using row-none or top. Here you can see two examples, one for Oracle and another for a non-Oracle database. This approach lets you take advantage of the database's native capabilities to fetch and gradually insert records into a data window. At the same time, it keeps you from bringing a huge dataset into the client just to filter it later. If you don't want to use database pagination, or simply prefer not to modify the data window query, you can implement record pagination through a web API. The most natural option for a Power Builder or .NET developer is to use the new .NET Data Store, which provides a more powerful API for data management, along with easy-to-use functions for any programmer. As you've seen, Power Builder 2025 lets you quickly create a CRUD web API directly from the IDE. All you need to do is select the data window objects you want to expose, run through the wizard, and it will generate a ready-to-run .NET solution with the project and code in place. Once you have this web API, you can customize it. For example, by adding a new function in the service and controller to retrieve data page by page. To do that, you call the retrieve by page function, passing the arguments, the starting record number, the page size, and finally the data window arguments, if any. For instance, if you want to fetch the first 10 records, you'll pass 0 and 10 as the first two arguments. 0 because in .NET indexing starts at 0, and 10 for the page size. Later, to retrieve the next 10 records, you'll pass 10 and 10. These values need to be provided from the client side, and they must be received by the controller and the service, along with any other required data window query arguments. And a second option for retrieving data gradually, page by page from a web API, is by using SnapObject's native classes, meaning without using the .NET Data Store. In this example, you can see how two SnapObjects classes work together: SQL Query Builder and SQL Executor. SQL Query Builder provides special functions to dynamically build the SQL statement, and it also includes a page function. This function takes two arguments, current index and page size, and gives us similar functionality to the retrieve by page method we just saw with the .NET Data Store. Once the query is ready, we generate the SQL statement with the toSQL string function. Finally, SQL Executor lets us run that SQL statement with the select function. This SnapObjects approach offers flexibility in structuring the result set, since it can use dynamic models to shape the final output. Another key aspect of optimizing the data volume in Power Server applications is the number of columns we retrieve in a result set, especially when working with large record sets. As the number of rows in the result set increases, the number of columns will cause greater degradation in performance, particularly in cases where your application uses nested loops that process rows in the outer loop and columns in the inner loop. A clear sign of unintentionally excessive columns is when you see SQL syntax like select asterisk from, or when a data window selects all the fields from a table, even though not all of them are required by the application. You should pay special attention to these cases when retrieving, for example, more than 50,000 records, and make sure to remove any unnecessary columns from your queries. It's also a good general practice not to exceed 100,000 records when interacting with the web API, not only because you don't often need all of them at once for a process or report, but also because some Power Builder objects that handle JSON content will call third-party libraries that are memory intensive. The last strategy I want to share with you is about one you could use to send a large volume of data from the client to the web API. This technique allows you to set a new HTTP header called multipart/form data, which you can use to send large structured data, blobs, files, or even a combination of them all in a single request. To configure this header, you'll use the Cloud App Set function with multipart form data min size as the first parameter and 0 both in string format as the second parameter to set the header to multipart/form data. Optionally, you can provide a positive value to define the package size in kilobytes. And if you want to restore the standard header application/JSON, simply set -1 in the second parameter. When multipart/form data is used, data will be compressed when sending from the client PC to PowerServer, so you can reduce network transmission time. However, be aware that this approach may require extra processing power and memory, both on the client PC and on PowerServer, to handle the data transformation. Make sure to carefully weigh the advantages against the potential drawbacks before deciding to use this option. We'll now review these cases in the tools. We have a new window, also with 3 tabs. The first tab is used to retrieve about 20,000 records. In the original client-server version, all data retrieved in a single call. In the workaround option, we gradually retrieve the records using a web API and the retrieve by page function of the .NET data store. Here we can see the implementation of both the service and the controller. In both cases, they receive the parameters current index and page size. For this, exercise is set to 10. Both parameters are sent from the client app, and the web API runs on the same server as PowerServer. The second exercise is about retrieving data in a data window, and it has 2 versions. The first version, the original one, retrieve all columns from the sales order retail table, while the second version, the workaround, only retrieve the required columns. Here we have both data windows which are switched using the data object property. The last exercise is about saving a video into a long binary field. This video is also displayed using the web browser control. In the original version, the data sent using a standard header application/JSON, while in the workaround, we use the multipart/form data format. Now let's run our app and compare the performance difference between the original version and the workaround. In the first exercise, we can see that gradually retrieving data can significantly improve the responsiveness experienced by the user when handling large data volumes. Now let's look at a second exercise. We can see that selecting only the necessary columns improved the application's performance. In this case, it was reduced about 30%. And finally, in the last one, we can see that sending a file from a client, in this case 30 megabytes, using the multipart form data format is slightly more efficient than using the standard JSON format. And that was my presentation. I hope I've given you some ideas to help you achieve solid performance in your PowerServer applications on the internet. Thanks to Appian for this opportunity, and I'm available for any questions you may have.
Now is Q&A time. Welcome to join our live Q&A Zoom meeting with the presenter. You'll find the Zoom meeting link at the top of the chat panel and also in the resources area below. Just click and join us live. You can enter the meeting from the Zoom app or your browser. Just type your name and click Join. You'll be in a waiting room until the meeting starts, and you'll join automatically once it begins. Now that you're in, you have 10 minutes to ask the presenter any questions about this session. Don't miss the chance.